Okay, so this next section should actually be pretty short. We're actually going to talk about what are called excitatory and inhibitory postsynaptic potentials. So first of all, neurotransmitters are specific for their receptors. This is something that you should already know. We've talked about this before, that acetylcholine receptors can only bind acetylcholine. Serotonin receptors can only bind serotonin. GABA receptors can only bind GABA. So neurotransmitters are very specific to their receptors. They will only bind to certain receptors. So a neurotransmitter can be stimulatory in one synapse, while it's inhibitory in another. So it depends on the type of receptor that's present. Okay? So you can have receptors for a particular neurotransmitter that can excite and stimulate that particular cell, or it can inhibit it or keep it from firing an action potential. So what you're familiar with is an excitatory postsynaptic potential. You're used to neurotransmitters that excite a cell and trigger an action potential, that promote an action potential to be sent. That's what happens with acetylcholine at the neuromuscular junction. It increases permeability to sodium so that it can depolarize the membrane so that we can reach threshold so that we can send an action potential. That's what excitatory postsynaptic potentials do. So neurotransmitters that display EPSP are going to be ones that cause local depolarizations that bring us closer to threshold so that when we do reach threshold, we can fire that action potential. So it is excitatory. It increases the likelihood of firing an action potential. It gets us closer to that threshold. So this is what an excitatory postsynaptic potential looks like. So basically again, it's just like what you're already used to. EPSPs, they bring the neuron closer to threshold. So in this case, you have a neurotransmitter binding to a chemically gated channel or a ligand gated channel. And what this does, it allows sodium to come in. That's going to cause local depolarizations, and that's going to get us closer to the threshold. Now you can see that you can see sodiums coming in. You can also see potassiums coming out. However, you're going to have sodium coming in at a much greater amount than potassium leaving. So you can see that here in this little description here. The electrochemical gradient for sodium is bigger than it is for potassium. So more sodium enters than potassium exits, and so that's going to result in our depolarization. So honestly, you can ignore the potassium part of it. These EPSPs, they're going to allow for these channels to be more permeable to sodium, so we can bring more sodium in so that we can get us closer to that threshold and get us closer to triggering an action potential. So on this, I would focus on the sodium. Now, an inhibitory postsynaptic potential, IPSPs, so neurotransmitters that display an IPSP. These are going to increase the permeability to potassium. So they're actually going to hyperpolarize the postsynaptic membrane. I'll show you what that means in a second. And they're inhibitory, which means that they decrease the likelihood of firing an action potential. So before we get into anesthetics, I'm going to show you what this looks like. So with IPSPs, what happens in this situation is you have a neurotransmitter bind, but that's not going to allow sodium in. What it's going to do in the case of IPSPs is that you have potassium leaving. So if you have positive ions leaving, you have positive things leaving, that's going to make your cell more negative. So these IPSPs actually lower the membrane potential, make it more negative, so that makes it less likely that you're going to fire an action potential. Because in this case, if we have this potential going down, we call this a hyperpolarization. You don't really have to know that word, but it's going to bring that potential down. So if we did want to fire an action potential, we would have to make up that negativeness that we just created with the IPSP, plus get from our resting to our threshold, okay, which is going to make it even harder for us to reach threshold if we actually start at a more negative starting point. So these IPSPs are when neurotransmitters make it harder for us to fire an action potential. So one thing that's inhibitory kind of in this way, not exactly in this way, are local anesthetics. So local anesthetics, well, first of all, on awareness of pain, the only way that you can feel pain is if action potentials are generated by the sensory neurons in the area in which you have that pain. So with local anesthetics like Novocaine, like things that they use for dental work, they act at the site of application to prevent pain sensations. And how they do that is by blocking voltage-gated sodium channels. So when we go back to this thing here, with local anesthetics, what happens is that they block voltage-gated channels. Right? They make firing action potential basically impossible, because what's going to happen is you already know that when we reach the threshold, we switch from our ligand-gated channels to our voltage-gated channels. But if those voltage-gated channels are blocked, we can never make that switch, and an action potential is never fired. Okay, so with the case of local anesthetics, it is inhibitory in the way that it completely blocks voltage-gated channels from opening, so we can never make that switch in order for the rapid depolarization to happen in order to keep that action potential going along the axon of that cell. So local anesthetics are inhibitory in that sense, that they block voltage-gated channels from being open, so that we can never make that switch in order to allow for the propagation of an action potential. So again, acetylcholine and that muscle physiology neurotransmitter we talked about, that's going to display an EPSP, where we have local depolarizations that do occur that get us closer to meeting that threshold. IPSPs will do the opposite. They'll make it so that our membrane hyperpolarizes or becomes even more negative, so that we have an even harder time creating an action potential. And, you know, that is actually good in the cases like local anesthetics, because if we want to stop us from being aware of the pain, we have to stop the action potential from being sent that gives us that perception of pain. So if we never have that action potential being sent to our brain to tell us to feel that pain, then we're not going to feel it. And the dentist can keep drilling away and doing whatever, and we won't feel that actual pain. Okay, so no EPSPs in the central nervous system neurons equals no perception of pain. Okay. So no action potential, no pain. I think I'm gonna stop there for that one. Told you that one's gonna be a very, very quick video about EPSPs and IPSPs. And then the last section that we have is gonna be on neurotransmitters. Yeah.